All right, I'm ready for one last mini lecture, and I'm taking all the odds and ends and I'm putting it into one lecture here. But I want to cover this last topic because I'm excited about learning about the Krebs cycle and how it might have originated. Because when you see all these steps, you're like, okay, Krebs discovered it through a certain number of steps. How could this have come about? And a lot of people ask this question, how could things have resulted? How could life have resulted from non-life? And my whole thing is, whatever the answer to that question is, it's a valid question to ask. And yeah, be skeptical about it, but don't be so skeptical that you throw out every answer before you even consider it. Nick Lane, in his book Transformer, has a very plausible set of reactions for how many Krebs cycle intermediates might have been produced from non-living hydrothermal vents. This is not fully worked out, it's just a proposal. But I want to say, I think this is interesting enough to pass on. And it's interesting enough to think about. I want you to see how each of these steps is plausible, and some are more plausible than others, that's for sure. So I want to look at this and this will also help you learn the Krebs cycle, because it's a Krebs line before it was wrapped around into a cycle that was formed by the Earth itself. The main thing about the Earth is that it's a dynamic system, right? And you have a lot of things on the inside of the Earth that want to come out, like a balloon leaking air. There's a lot of hot gases and a lot of rocks that are inside the Earth. Geology moves all those around. At the bottom of the ocean, they have these vents where the hot gases come out. And what really shocked them about finding those vents was when they went there, you see all these red and white worms, really weird forms of life, living far down from the sun. No photosynthesis here, at least not from sunlight. There could be photosynthesis from IR light that is emitted by the hot materials. That's another story for another day. We know that these things are living. We didn't think it could happen. Here they are. Could this be a clue to how life got started? And if this is the case, by the way, then life started according to the laws of chemistry. And it's not necessarily just a fluke accident. It actually says something about how we seem to be meant to be here. That chemistry actually puts things in order that leads to life, that leads to you and me having this conversation right now. So how can this major step from non-life to life, how could it happen at this sort of place where the Earth seems to be living a little? There's constant flow, there's constant gradients, there's constant motion chemically. There's interesting things going on, and life can exist here. Could early life exist here? When you look at this, there's a lot of the ingredients that you need that actually are found in the Krebs cycle. And I think there's enough clues that it's very suspicious. I actually wrote about this in my book. There's a chapter, and I titled it deliberately, 7 Clues About the Origin of Life. Because nothing's really definitive here. But maybe if there's an experiment, it can be definitive. If you look at these, there's white smokers and black smokers. The black smokers have more chemicals in them, and they're probably more interesting. And there's one particular rock that is found there. It's mafic rocks that are turned into serpentine. So it's called serpentinization. When you have rocks being turned into this cool green, it looks like serpent skin. That's what it's named for. The important thing is when these rocks are made by the vent's action on other more common rocks, hydrogen is given off in abundance. Basically, you have, and hydrogen is full of electrons. We still use a form of hydrogen whenever we're using NADH or FADH2. Those are a complicated form of hydrogen. They're using the electrons. Just like hydrogen carries electrons, those carry electrons. Could hydrogen have been the original electron box? We have a bunch of it being produced here, and we have a bunch of life living there. If you look at the bottom of this black smoker figure, you can see a little thing of pyruvate. Remember that pyruvate is very central. It's a very interesting, for only having 3 carbons, it's a very interesting molecule. So let's take a closer look at this. And what I'm going to want to do is I'm going to want you to play a game with this. I'm going to give you all the reactions right now, and we're going to do an exercise on Monday in class. So I want you to listen through this, and then I want you to do it with your hands so you learn what goes on. The Krebs line can basically turn all the components. The game board is like the thermal vent, and it's producing the game pieces, which are the chemical products of the vent. And you also have, the vent has a complex structure, so you have like little bubbles in the rock, right? So you can have one bubble that's acidic and one bubble that is alkaline. You can have one bubble that has lots of electrons and another bubble that's electron poor. And you can actually have movements of electrons through the metals in the little side of the rock. This is an idea that the geology of rocks themselves might have provided chemical reactions that led to the Krebs cycle. To see how it works, I'm going to have these 4 colored pieces that move around on the game board. These are not floating in solution. These are next to a rocky surface that is pyrite. We mentioned that before. Iron sulfide is pyrite surface. So think of that as the game board. It's also got a little nickel mixed in, because nickel can react with H2 to pull the electrons off of it. If the electrons are pulled off, where do they go? They could actually go through the wall to another compartment, and you can actually have a redox gradient where you have electrons flowing through, as well as you can have hydrogen flowing through, electrons flowing through, and all the different forms of carbon flowing through, all the way from oxidized carbon to reduced carbon, CHO to CH4. So I'm going to color oxidized carbon purple. I'm going to color reduced carbon green. I'm going to color oxygen atoms red. That's the typical color, negatively charged. And I'm going to color hydrogen brown. And realize that this can be H plus as a proton, or more commonly it can be H bound to electrons, especially if you have thiols around. The iron sulfide can actually form thiols. The hydrogen plus electrons can bind to the sulfur in FeS, just like it can bind to cysteine, just like it's in lipoate. So you see how all these pieces, so we have these 4 colors of pieces, and remember that we can have different compartments that have acid or base, and also we can have thiols floating around. From these 1, 2, 3, 4, 5, 6, 7 ingredients, including the pyrite, you can actually form a reasonable pathway to get all the way to citrate. It might not be reasonable to go all the way to citrate, but I want you to see the whole thing. So I'm going from a paper published by Nick Lane, shown at the bottom. Please do go to that if you are interested. That's where I get these figures from. Then I get other figures from his book, which was published after the paper. The book is called Transformer. So the paper shows this, and you see the iron sulfide surfaces. You see iron sulfide coordinating with carbon dioxide, and it actually, under high temperatures and pressures, it actually can break it apart into a red oxygen and a purple COO, so carbon monoxide, oxidized carbon. And then you can have all those hydrogens floating around. So you can see this break apart that the surface can do. This makes our red piece and our purple piece. Then you see how the brown pieces, like the brown hydrogens, can also bind to the surface and move around, and all these electrons can go around. Eventually, ultimately, you can have some of those electrons going on to some of the carbons. So you can have a mixture of oxidized CO, purple, and reduced CH3, green. What's really cool, so you have this mixture and you have all these pieces on the board. And they're all attached to the surface, so they're kind of like milling around, like a crowd. This is the key reaction. This might look like kind of weird organic chemistry, but it is known to happen. I believe it's the Fischer-Tropsch, I can't say it exactly right, but it's something like that, reaction that they use to make, they use syngas to make other things. Anyways, industry knows how to do this reaction. And so what happens is that you can bond a carbonyl, you can insert it into a carbon bond, and you can actually insert the carbonyl between the carbon and the metal to form the carbonyl with the acetate group. You can see that right there. That is the cool chemistry. Carbonyl insertion, follow the purple, and it makes a carbon-carbon bond with an O on it that can undergo other chemistry, like a thiol can react with it and form a thioacetic acid. It can form a thioester. Isn't that suspicious, So you have this arrangement right here. The carbonyl insertion is the main thing. You have these 7 different elements, or not elements, but 7 different chemicals that are all floating around and reacting. So if you have that insertion, the initial insertion can create an acetyl group. Then you can actually insert again. You can have another, so there's the green carbon sticking off the end. You can just do a second insertion on top of the first one, and you end up with a pyruvyl group. Look at that. If you have basically if you can pull off that one hydrogen, the CH3, can turn it to a CH2, you can make the enolate version of pyruvate. That's the thing in the lower corner, enol pyruvate. And all that happens at that point, you make a lot of it, because once you pull the H off, the H can combine with acid to form H2, which bubbles away. Once it bubbles away, you can't do the back reaction. So you have just made this version of phosphoenol pyruvate. It's just without the phosphate. But you have this incredibly powerful enol bond. And it's that bond that, if there's nothing else I want you to remember from this, making that bond is the key to the whole thing here. Remember that we have all of these just from the gases, the carbon gases and the methane gases and the hydrogen gases bubbling up, constantly passing through the system. And so this is a really powerful molecule, as you know from the Krebs cycle. So the CH3 can't usually react, but the CH2 can, and the enolate has a CH2. For example, let's do another enol insertion, except this time we're not inserting next to the CO, we are inserting next to the CH. And if we do that, so the enol pyruvate can sort of, its electrons can sort of attach it to the surface, and then you can do an insertion just like before. Here's our purple insertion. And look what you make. If you do the insertion on the enolate end, you make oxaloacetyl group. All that you need is an oxygen to roll along and sort of attach, and then oxaloacetate floats out into solution. That insertion will make our oxaloacetate molecule, which seems to be a pretty key molecule in the whole process. There's oxaloacetate. From there, you actually can get from oxaloacetate back to succinate pretty easily. We would oxidize it in the citric acid cycle the way we run it, but it's pretty straightforward to just turn that around and to actually reduce it. In fact, you can argue in this environment that it would actually reduce better. So look at the top here. By reducing it, you have hydrogens from the surface that are attacking the partial positive on the CO oxygen. And by the way, this is the vulnerable one. The COOs at the end are acidic groups. They're more stable, and there's less you can do with them. They're basically bookends, but they help to hold it down to the surface. So in the middle, you can attack at the CO in the middle, and then you can make a COH. Then he shows it this way in his book. He shows the malate being attacked by the surface, and then he shows the this being protonated and the water flying away. Which again, you have something flying away, although there's a lot of water around, so I'm not that convinced by this step as much as being a big driving forward. But you do have the loss of the OH, and this is exactly like what we see in the citric acid cycle, except it's not. We're missing a piece. So take a second, pause if you need to, and ask what is missing from this picture. Which intermediate is missing? And what does that intermediate look like? Okay, now I'll tell you. The answer is it's fumarate. Because what happens is actually when the water leaves, the electrons don't actually just hop up at first. He's combining 2 steps here. When the water leaves, the electrons actually hop down and they form a double bond in the middle. And that is fumarate. He's not showing that. And then later, electrons hop back onto the double bond, except they form 2 CH2s and you have the succinate molecule. This is why I want you to do this. I want you to see this and see, if you see somebody going from malate to succinate, you should say, oh, wait a second, you're missing something. You're missing fumarate. In his paper, he actually shows fumarate, and so I'm going to show you that from the paper. This is malate, and he's showing it being protonated. It's being protonated by a thiol. I don't really care about those details. You just need to know that it's protonated, the water leaves, and it leaves behind a double bond. And then the double bond is reduced by the extra electrons and hydrogens that are coming up from the nickel that is pulling electrons off of hydrogen. By the way, you need a wall for this. This doesn't work if it's on the same side, but it does work if it's on the opposite side. And electrons can be conducted by metals, so it makes perfect sense that you would have a little membrane like this and the electrons would move across it. It's just a membrane of rock, not a membrane of lipids. And this makes succinate, but this is something that you, with your advanced biochem knowledge, can supply to his abbreviated version in the book. Now, what I find interesting is the book stops here, the paper keeps going. And yet the book was written after the paper, so I'm like, why didn't you keep going? I think he's less certain of the next two steps. But of course, I have to show you because I want you to see them and make up your own mind whether you think this could happen or not. Basically, he was able to propose steps that would take us all the way to isocitrate, technically not citrate itself. And but he does make a C6 molecule from a C4. So the paper shows that actually the succinate can react with a thiol to form a thioester, thiosuccinate, which is exactly like succinyl-CoA. This would react very well. The thioester is very reactive. And yeah, I could see this happening. And then when you have that, you have another carbonyl insertion that goes on that will make two COs in a row. It's a little hard to do, but if you have a thioester, that makes it easier, right? So you make a 5-carbon molecule, and lo and behold, if this molecule gets attacked by an alkaline type thing, then you actually end up with an acid group on the end, and you end up with an alpha keto group to that acid group. 5-carbon molecule, alpha keto group, alpha ketoglutarate. So we have that right there. There's the other carbonyl insertion. There's our little purple CO molecule. And it makes that. And then, well, this is the thing that I think he's really not sure about. But he basically proposes, well, we've gotten to C5. Why don't we go to C6? And in fact, because we have that alpha keto group, maybe the middle carbon between, in the whole C6 strand, we have the middle carbon able to react, the C5, the middle of the C5, is able to react. If a sulfur pulls an electron off there, then we have a double bond left behind. The enol it's actually enol-like chemistry. This is like the dehydration chemistry, actually. But you basically have the middle carbon is made vulnerable by oxidizing it. Then you can have an insertion there. You can have your little CO going in there. And then that forms a COO. That forms a oxidative group. And then you just reduce the COO that is next to it to make COH, and lo and behold, you have your isocitrate. It's probably not that big of a deal to say, okay, then the OH can move over, but there's not a really good chemical rationale for forcing it to move over at this point. And honestly, this stretches my credibility a little bit to get to this point, and yet, so I think the succinate's pretty solid. The path to succinate. The path past succinate, make up your own mind, it's less solid, but maybe do some experiments to get back to me. If you can see some of this happening in solution, it will help to convince me. So he does all these words, and these are too small for you to read right here. But I want you to go through this process, and I'm going to walk you through this process in class so that you can think about what the Krebs line means, because it helps you understand what's going on with all these different intermediates. You'll really know the intermediates well, and that's what I want you to know. And the main point is he makes this point, and I make this point in my book. There's only so many ways that chemistry can react to form stable molecules. There's only so many ways it can form unstable molecules that will hold energy in a sense. So from these ways, there's reason to believe that maybe we can recreate the path that life took. If life was sort of encoded in chemistry, maybe there's a puzzle here that we can work out, just like Krebs worked out how the cycle worked in the first place. Maybe we can work out how the cycle was made. And to me, that doesn't diminish things at all. It just is something that we are given. It's a gift. that we can understand in this way. Don't let that diminish your sense of wonder or amazement at the whole thing. A gift that you can understand is in some senses better than a gift that you can't understand. There are only some things that you can't understand, but this might be one of them. So basically, if this is true, then maybe chemistry has a path to life. And maybe if it happened here, maybe it could have happened on another planet. Or maybe it was very, very, very unlikely. That's the question. This makes me think it's more likely. At the very least, we have a logic that we can follow, and that's what I want you to learn. All right, so thanks for bearing with me on my little hobby horse about all this, but I want to cover this because this is why I like biochemistry, and I want you to know why I like it. All right, I'll see you on Monday to talk about this, and yeah, whenever you're watching this, hopefully we will work on learning it.